All right, so today we're going to talk all about isomerism. What does it mean if I say that something's an isomer? We talked about this, I think, first or second week. What is an isomer? Same molecular formula. So an isomer is something that has the same molecular formula. So we've talked about these already. Primarily, we've talked about constitutional isomers, right? Where you have the same molecular formula, but the atoms are actually arranged entirely differently. So let's kind of make a tree showing how these are all related. And I'll put isomers at the top, and then I'll write same molecular formula. And then these get divided into two subclasses. One, we said, is constitutional isomers. And these are molecules that have different connectivity. All right, so let's take an example of this. We said in class you could have something like ethanol, and we could compare this to dimethyl ether on the right. Which one's going to have the higher boiling point? The one on the left or the one on the right? Why the one on the left?
Hydrogen bonding.
Hydrogen bonding, exactly. So constitutional isomers have completely different reactivity. They have completely different physical properties. They're nothing like one another, right? They're attached completely differently. We do have another class of isomers where they are connected in the same way, but they have different properties. And these are referred to as stereoisomers. All right, let's try again. So same connectivity. But it has a different 3D layout. So these are different than constitutional isomers because the atoms are connected in the exact same way, but they have a different layout. Within stereoisomers, we have two different subclasses, though, because nothing's easy. So we've got enantiomers over here. And enantiomers are pretty easy to spot because they are non-superimposable mirror images. In fact, we talked about enantiomers already when we were talking about plane polarized light, right? We said one enantiomer will spin light one direction, the other will spin it the opposite. So let's take a look at an example. So a good example might be this compound. What would this be called? Yeah, trans 1,2-dimethyl cyclohexane. If we were to draw the mirror image, I'll just make a little mirror image here. Whoop. If you make these two models and you try to overlay them atom for atom, you can't, right? It is impossible. So these would be an example of a set of diastereomers, or sorry, enantiomers. I'm reading ahead. Diastereomers are different, all right? So the question is, how are enantiomers and diastereomers different from one another?
Diastereomers are not, they are mirror images, but they are superimposable.
Not quite. So if you have a mirror image and it's superimposable, those are just identical molecules, right?
Yeah.
So really the only difference between enantiomers and diastereomers is enantiomers are mirror images, diastereomers are not mirror images but have the same connectivity. So not mirror images. But same connectivity. And I'll show you guys a common example you may have seen already in some of your chemistry courses. Let's say I've got this alkene This is a cis alkene, meaning both methyl groups are coming off the same side. And if you compare it to this one, it's a trans alkene, right? They're coming off of opposite sides. So cis and trans fats have different properties. You know that because one's good for you, or at least not bad for you, and the other one has really negative health impacts. So these are very, very different from one another, and you can tell it's the same connectivity of atoms. We still have a double bond between the two central bonds, but we have a different three-dimensional layout of each of them. So these are very unique from one another. So let's make a little note on how all of these are different. And down here I'm going to write down, all right, constitutional isomers. These have different physical properties. And these can be easily separated from one another. Enantiomers are a little bit more difficult. They actually have the same physical properties. And that means that they are difficult to separate. So what do you think I mean by physical properties? What would be an example of a physical property that we could use to separate things with? Boiling point, right? So for example, in lab, we can separate things by differences in boiling point by using distillation. You can do that really easily with constitutional isomers. You can't do it at all with enantiomers. They have the exact same melting point, exact same boiling point, exact same physical properties. In fact, the only way we can actually tell them apart in lab is with that plane polarized light, or the polarimeter.
Do all stereoisomers have the same physical properties?
No. So that gets to the next one, diastereomers. So diastereomers are another set of stereoisomers. And we said that diastereomers are not mirror images but have the same connectivity. These ones, again, have completely different physical properties. So if you have a set of diastereomers, you can separate them using distillation or differences in polarity or things like that really easily. Enantiomers are the super duper tricky ones. Does that make sense? All right, so now what we're going to do is a little bit of problem solving here. And I'm going to ask you guys to help me with some of this. What I'm going to do is I'm going to give you a molecular formula. I'm going to ask you to draw all of the isomers for that molecular formula or compound. And then once you've done that, I want you to determine which of them are chiral or achiral, meaning achiral is not chiral. And if an isomer has a stereocenter, designate it as R or S, and then determine the relationship between the pairs of isomers. So there's a lot going on here. Focus on going through these sequentially. So for our first example, C3H7Br. Let's try to figure out how many different isomers there are for C3H7Br. Draw those out, and we'll determine if they're chiral or achiral, and then designate any stereocenters as R or S. So I'll give you guys a minute to work on that. You can do it in bond line. All right, give me a thumbs up if you think you've got all of the isomers. Show me with your fingers how many you think there are. Seeing some 2s, some 7s, some 3s. All right, let's try this. I want you guys to help point out any mistakes that I might be making. All right, so the easiest thing to do is write out my carbon backbone, right? It's 3 carbons, and I'll just put a bromine off the end. That's an easy one. Well, all right. What if I move that bromine to the second carbon in? I'd say that's unique, right? All right. What if I do all the way over to that left carbon?
That's just the same as the first one.
It's the same as the first one? Why?
Just flip it over.
Yeah, all I did was flip it over, right? And if we were to name them, what would they both be called, the left and the right one? Yeah, they would both be 1 bromopropane. I could draw it a million times, it wouldn't make it any more right, so I'm just going to erase this. Are there any others? No, I'd say these are both unique isomers for C3H7Br. All right, the next thing was to determine whether or not these are chiral or achiral. What do you guys think? Do you guys think any of them are chiral?
No.
No, I'd say if we tried to draw their mirror image, it wouldn't be they would be superimposable, so it wouldn't be chiral. So let's make a note. Both of these are achiral. Usually at this point, though, somebody will stop me and they'll say, all right, but Jeff, what about this versus that? Are they the same or different? They're the same, right? It's just one flipped over. So you can show it as a dash or a wedge. You don't have to unless you really want to because it doesn't mean much. All right, so we know both of these are achiral. And I'll just put this down here and I'll write this is the same thing, right? All right, if we look at the relationship between these two potential isomers, how are they related?
Constitutional.
They're constitutional isomers. Will these have the same physical properties or different? Different, exactly. So these are both achiral. They have different physical properties. They'd be really easy to separate. Let's try a harder one now. All right, the harder one now is C4H9Br. Let's see a show of fingers. How many isomers are there? Seen some 3s, 4s, 2s. Oh man, there's actually 5 that I got. See if you can find 5.
Is this where dashes and wedges come in?
Yeah, you might need dashes or wedges if they are truly different. Does anybody think they got all 5? You guys want to do this together? All right, let's try this. I'll start with the easy one. So we'll do a 4-carbon chain. So 4 carbons, and I'll just put a bromine off the end, right? Pretty easy. All right, next one, I'm going to put bromine 1 carbon over. So right there. Are there different ways to draw that, though? Yeah, one a wedge, one a dash, right? Because if we look at it right now, right there we have a stereocenter where that red star is. So I'm going to show this bromine on one of these as a wedge. And then on the other one, I'll do a dash. All right, what if I do the bromine 1 carbon over to the left from where it is now? They'd be the same, right? Because they'd both still be 2 bromopropane, whether or not they're R or S, doesn't matter. All right, let's try doing some more isomers. I would say this would be another one, right? And then last but not least, see how they're all different though? So let's try to name them, right? So for example, with this one, our longest carbon chain would be 1, 2, 3. So this would be 1 bromo, 2 methyl, propane. Where the one on the right would be 2 carbons long. So this would be 1 bromo.
The one on the right doesn't have too many hydrogens.
Nope, it still has 9. They all have 9.
Would be 3,
1 dimethyl ethane. Oh, I'm running out of room here. And all of these have 9 hydrogens on them, right? And we know that they're different because they have different names. Does that make sense? Does everybody kind of agree on that so far? All right, so now we've got to go back and determine whether or not these are chiral or achiral. And I'm just going to erase these numbers for now. So how many of you think the one on the far left is chiral? That's good. It's not chiral. What about the next two? Yeah, definitely. So I'd say these are chiral. Chiral. This is achiral. This is achiral. And achiral. All right, next thing was to designate stereocenters as R or S. We know that we've got two stereocenters for the middle two chiral compounds. Which one's R? Is it going to be the left one or the right one? Yeah, I'd say the left one, right? So really quickly, we could say priority 1, priority 2, priority 3. We go clockwise around. Lowest priority is a dash, so this is going to be an R. So I'll just go ahead and label this as an R. This one must be what then? An S. So not too bad. All right, now what we need to do is determine the relationship between these isomers, right? So first one and second one, how are they related?
Constitutional.
Yeah, constitutional isomers. So these will be really easy to separate. They have very different physical properties. What about these two? They're stereoisomers, right? They have the same connectivity.
But they're diastereomers.
Are they mirror images of one another?
No.
I don't know about that.
So they're
It depends where you place the mirror, right? So if you have the mirror right in front of the one on the left, it'd be the same as the one on the right. So they are, in fact, mirror images of one another, which means these would be what? Enantiomers. Again, this is a situation where a model kit can come in handy if you're having trouble seeing that mirrored relationship. Build both of these and then hold them up against one another in different ways to see if they are mirror images. All right, and then last but not least, I'll just do a couple more. What about these three? How are they related? Constitutional isomers. Oop. Does that make sense? The relationship between all of these? Let's try an even harder one then. All right, the next one, instead of giving you a molecular formula, I'm going to just give you the name. All right, so on the 2 position, I've got a bromine. 3 position, I've got a chlorine. How many stereocenters do I have? 2. I've got one right here and right here. So 2 raised to the second power should be 4 total isomers. All right, so let's try to figure out the number or the different types of isomers that could account for all 4 of them. Show of thumbs, who thinks they got all 4? A few people? Show you guys how I typically handle this is I just start out doing both wedges. Then I'd say, all right, let's do both dashes. And then what would I do next? 1 wedge, 1 dash. Or I could do the bromine off of a dash and the chlorine off of a wedge. All right, now what we need to do... Oops, sorry, this should be a chlorine. All right, now what we need to do is determine which of these is chiral and achiral. What do you think? Well, first of all, if I go through and I look at these, I'd say they all have stereocenters, right? At these red dots, that's why we have 4 total. Is there a plane of symmetry for any of them?
Nope.
Nope. So they must all be chiral, right? So they are all chiral. So all isomers are chiral. So let's designate their stereocenters as R or S. So for example, let's do this front one right here, the bromine stereocenter. Is that going to be R or S? Highest priorities of bromine, R. Okay, so anytime the bromine is a wedge, as we have it drawn, it's going to be an R. All right, which means these other bromines must be what? S's, right? Pretty easy. All right, let's do the same thing with chlorine. Is that chlorine going to be an R or an S?
That was R.
An R. All right, that means that anytime that chlorine's a wedge, as we have it drawn, it'll be an R, which means these middle two must be S's, right? All right, so now we've got them all labeled. We've got one that's RR, we've got one that's SS, we've got one that's RS, and then one that's SR. Okay, so these are all unique stereoisomers, I would say. Now we've got to determine the relationship between each of these. So let's start with this first one. What do you think the relationship is going to be between those first two compounds? Enantiomers, right? They're actually mirror images of one another. So an easy way of doing this, again, would be to get your model kit. And so, for example, I'm going to do bromine as red. I'm going to put it in the front. And chlorine as green. I'm going to put that in the front. Do I have a helper that wants to hold?
I'll help. No, I'm going to use that, but I guess so. I got it up already.
Got a track before you could leave. All right. So you got that one there. Let's do the opposite one. All right, do you want to actually move over a little bit? Can you guys see how these are both wedges? And with mine, they're both dashes. All right, now what we need to do is see if we can arrange these so that they're mirror images of one another. And can you guys see how, kind of holding them like that, they are mirror images of one another? So they are definitely mirror images of one another, and it can be a little hard to see unless you actually build the model. But you can have a mirror going in and out of the page or in line with the page. So these would be a set of enantiomers. All right, let's try the next two. What's the relationship between those? Yeah, I would say they aren't mirror images anymore, right? So these would be diastereomers. We're not going to use cis or trans right now. We're just going to use enantiomers or diastereomers. All right, and then let's do the last two over here. What's the relationship between those last two? Again, they're going to be enantiomers or diastereomers? Enantiomers. I'll show you guys a super duper handy trick. Oh, come on. If you have stereocenters, and all of your stereocenters are flipped, that means that they are enantiomers. So if we go back up and look at those right two, you see where the bromine's coming off of? The third one in, it's an R, but the last one, it's an S. So we flip that stereocenter. And then for the chlorine, it was an S, and then it becomes an R. We flip all of the stereocenters to the opposite one. So the key word in this is all of the stereocenters are flipped. All right, let's talk about diastereomers. Oh my goodness, sorry, I'm going to figure this out tonight. If some, but not all, are flipped, that means you have diastereomers. So the key word again is not all, just some. are flipped. So this is a really helpful trick, especially with students that have trouble imagining things in 3 dimensions and visualizing mirror images. Just go through assigned stereochemistry. If all your stereocenters are flipped, you know you've got a pair of enantiomers. If some are flipped, but not all of them, you've got diastereomers. Make sense? Let's try one more challenge one. All right, for this challenge one, we're going to do 2,3 dibromo butane. So again, we want to figure out how many potential stereoisomers we have, and then go through the list of determining whether or not they're chiral or achiral, assigning stereochemistry, and then assigning isomeric relationships. If you think you got all the isomers, give me a thumbs up. Show me with fingers how many you think there are. See some 2s and some 4s. Let's check. All right, so again, I'm just going to do my backbone. I'm going to just arbitrarily pick them both as wedges for my first one. I'm going to pick both as dashes for my second. I'm going to pick one as a wedge here, and then one as a dash here. And then same thing, I'm going to pick first one as a dash, second one as a wedge. All right, so there's theoretically 4 different ones. Does anybody spot anything unusual though? Are the first 2 the same? A little bit tricky. So let's think about it this way. I'm just going to pick this one, right? And I'm going to rotate it along that sigma bond. And if I rotate it along that sigma bond, this bromine on the left will still be a Br. What about the one coming off this carbon? If I rotate it, it'll be a dash, right? What do you notice about that molecule? Symmetry, just like our pod, right? So if we look at this, what sort of compound would that be? Be a meso compound, exactly. So if we look at this one, it'd be a meso compound. So this is achiral. What about this one right here? It'd also be meso. So all right, achiral, meso. What about the ones on the left? You think they're going to be chiral or achiral? They'll both be chiral. All right, so let's go through and assign stereocenters right now. So for example, this stereocenter where I've got the bromine as a wedge, will that be R or S? Should be R, right? Which means this one must also be an R. And what about the ones where they're dashes? S, right? And let's do this one on the first one, the other bromine. What will that be? Should be an R, right? Bromine, if we look at it, should be number 1, followed by 2, followed by 3. So we go clockwise around. Lowest priority is a dash. So this would be R, which means this one over on the far right must also be an R. And right here and here, because they're dashes, they must be S's. All right, do we agree on that? Now the tricky part. Assigning enantiomers and diastereomers and isomeric relationships. So let's just pick this one and that one at first. So the first 2. What do you guys think? Enantiomers, why? Yeah, exactly. Both stereocenters have been flipped. So these must be enantiomers. All right, next one. We've got these two. What will they be? Diastereomers, because only one stereocenter was flipped. All right, and then these two. What's the relationship between them? Well, let's look at it, right? It's a little bit tricky. It's super tempting to say that they are enantiomers, right? Because it looks like we flipped every stereocenter. But let's try building these. Again, I might need some volunteers to help me hold this. Does anybody want to come up and help me hold the model kit? Okay, so I'll build the one that's third one in. All right. And then I'll do this one over here. All right, can you guys see that that's the two molecules that I've got shown there? Do we agree on that? Let's try to rotate them around and see if they're the same or different or how they're related to one another. I see that they're exactly the same compound. It's super duper confusing, but because they are meso compounds, we already knew that, they are identical on their mirror image. So they are the exact same compound. So meso compounds do not have enantiomers. Does that make sense? Because we know the enantiomer of a meso compound is the same thing, right? So while I did draw 4, really we didn't need to draw 4. There are only 3 unique isomers for this compound. All right, let's try another one. Let's try this. Whoop. These two. So first and third, what's the relationship between them? Yeah, diastereomers, definitely, because we did flip one, but we didn't flip the other. So the number one mistake I see people make in this class is on exams, they feel rushed and hurried and they forget to identify meso compounds. If you can spot that internal plane of symmetry, it'll save you a lot of heartache later on when you're asked about chirality and whether or not there's enantiomers. I'll show you a good trick for spotting meso compounds, though. What's the first one that I already told you guys about? Internal mirror plane, yeah. Internal plane of symmetry. And then each stereocenter is opposite stereochemistry. So for example, if we go back up and we look at the achiral meso ones, do you see how the bromines are R and S on each of them? That's an easy way to spot an achiral compound is we know it's symmetric because each bromine's kind of equidistant along the chain and they have opposite stereochemistry. So that's a really quick and easy way of spotting a meso compound if you have trouble visually changing it or rotating it. What's that? Yeah, exactly. So you see how both of them have bromines coming off the 2 and 3 position? One's R and one's S. That's a really quick and easy way, where the other ones were RR and SR. Or RR and SS, excuse me. All right, does that make sense? A little bit tricky. All right, and then last but not least, we get to do some easy review. Cis-trans isomerism. This is referred to as geometric isomerism, and it is not absolute. So I'll show you guys an example of this. Is the one on the left cis or trans? And what would its name be? Cis, right? Both methyl groups are coming off the same face. So this would be cis, 1,4, and then what? Yeah, dimethyl, cyclohexane. One on the right would be trans, 1,4, dimethyl, cyclohexane. All right, second question. Are there stereocenters in each of these? Why not? Why isn't this a stereocenter on the top? I have a wedge, Sean. Yeah, there's not 4 unique substituents. If we look at the ring and we follow the path around the ring clockwise or counterclockwise, it's the exact same path. So there are no stereocenters in here. All right, second question. What's the relationship between these? Are they mirror images of one another? No, they are not mirror images. They're connected in the same way, right? They're still 1,4 dimethyl cyclohexanes, but they're not mirror images, which means they must be what then? Diastereomers. So occasionally as chemists we run into this problem where we can't assign stereochemistry, but we still need to designate it as cis or trans because they are 2 unique compounds. If possible, if you can, use R or S instead of cis and trans, but if you're in a situation like this where you can't designate R or S, then you're forced to use cis or trans. Does that make sense? It's kind of a weird situation, but we do need to be careful to designate stereochemistry using cis or trans here. All right, I think that's where we'll leave off today. Tomorrow when we come in, we're going to do a bunch of in-class practice because this section in particular really trips people up. So I'd recommend spending a fair amount of time on your pod tonight and make sure that you come to class tomorrow ready.